We were talking about what a buffer is and how to calculate pHs. Now we're going to talk about considerations in making a buffer. One of these is the relative amounts of acid and base. That's a factor that influences the effectiveness of the buffer. So a buffer is most effective when the concentration of acid and conjugate base are equal. So we'd like the concentration of the acid and its conjugate base to be equal. So let's look at two 1-liter solutions of a generic buffer that has a pKa of 5. And we'll calculate the percent change in pH when 0.01 moles of sodium hydroxide is added to each. So here we have solution 1, 0.1 molar in HA and A minus. Solution 2, we've got 0.18 molar HA and 0.02 molar A minus. So here's the initial pH is 5. Here it's 4.05. So again, I don't like this. So we're adding 0.01 moles of sodium hydroxide to this acid. So we're going to look at the stoichiometry here and see, well, what's going to happen here? Well, the hydroxide is going to react with the acid. Which one is limiting the reactant? Limiting the reagents? No. Which is the limiting reactant? That's what I meant to say. The OH minus, because this is smaller, right? So all of this is going to react. So we're going to subtract all of that. And we're going to subtract that same amount from this one, which will give us 0.090. And then we're adding that over here. Does that make sense? We're not worried about the equilibrium here. We've added something to the solution. We're going to assume that the reaction occurs completely, and then we deal with the equilibrium. So these are the moles of substances afterwards. And I believe this was a 1-liter solution. And so how could we calculate the final pH of this buffer solution? Henderson-Hasselbalch equation, right? So the pH of a buffer solution is equal to the pKa of the acid plus the log of the base concentration divided by the acid concentration. So here we have doesn't give me the pKa. Did I do back here? Yes, pKa is 5. So the pKa is 5 plus the log. This is 1 liter of the solution, so the concentration of the base is 0.110 moles per the 1 liter. And the concentration of the acid is 0.090 moles per liter. And again, if you prefer to do an ice table, that always works. So 5 plus the log of 0.110 divided by 0.09, and that's going to give me 5.0872 or 5.09. So over here, looking at the second solution, again, we're adding the same amount of hydroxide, so 0.010 moles of sodium hydroxide, and this time we have 0.18 moles of the acid. So this is still our limiting reactant, so we're going to subtract that, and we're going to react out the same amount of the acid, and that will create that amount of the conjugate base. So now we have 0.03 moles of conjugate base and 0.17 moles of the weak acid. This is the same weak acid, so the pKa is the same. So we've got 0.030 molar divided by 0.010 molar. No, that's not right. I was looking at the wrong box. This is 1.7. So the calculator is giving me, 4.2467, which would be 4.25 as my pH. The initial pH was 4.05. Adding hydroxide, we expect the pH to go up, and it does. So this one increased from 5 to 5.09, right? So that's I think it was asking, I forget. Yeah, it's asking for the percent change. So the percent change will be the difference, 5.09 minus 5.00, divided by the starting pH. So that's a change of 1.8%. And this one, the percent change, will be 4.25 minus 4.05 divided by 4.05 times 100. That percent change is 4.9%. So this is illustrating the effect of relative concentrations of the acid and its conjugate base. We have the same total number of moles here. 0.1 and 0.1 is 0.2, and if we add these together, we also get 0.2 moles total, right? But for this one, we got a 1.8% change in pH, and this one a 4.9% change in pH. That's significantly larger. Any questions? So you can better buffer your pH if the amounts of acid and conjugate base are equal. So equal would be ideal, but we could also look at reasonably effective. In order for it to be reasonably effective, the acid and conjugate base concentrations should not differ by more than a factor of 10. So the acid could be 10 times larger than the base, or the base could be 10 times larger than the acid. But if you go farther than that, it's just not really going to be effective. The absolute concentration, not the relative, but the absolute concentrations are also going to affect the capacity and the effectiveness. So a buffer is most effective when the concentrations of acid and base are high. We're going to look again at that generic buffer. But now solution 1 is going to have concentrations that are 10 times higher than solution 2. Again, we're going to calculate the percent pH change. So let's just erase these things that I don't like. So here we're adding 0.010 moles of hydroxide. That is smaller than 0.5, so all of the hydroxide is going to get used up, neutralized by the acid. So we're going to use up 0.01 moles of the acid, leaving us with 0.49 moles. And that's going to create 0.010 moles of the conjugate base, so we end up with a final amount of 0.51. So again, Henderson-Hasselbalch equation, the pH is equal to 5.0 plus the log of the base concentration. So here that's 0.51 molar. Remember, these are in moles, but we are talking about 1 liter of solution. And then this is 0.49 molar. So 5 plus the log of 0.51 divided by 0.49. Our new pH is going to be 5.0173 or 5.02. The percent change will equal 5.02 minus 5.00 divided by 5.00 times 100. Or 0.4%. Let's look at solution 2. Again, we're adding the same amount of hydroxide, 0.01 moles. And this is still smaller than the acid concentration. This acid concentration is 10 times smaller, right? It's 0.05 instead of 0.5. We're going to react all of the hydroxide. That will react the same amount of acid, leaving us with 0.040 moles. And it will form 0.010 moles of the base, giving us a total of 0.06. So again, the pH is equal to 5 plus the log of the base divided by the acid concentrations. There the pH is now 5.176 to be 5.18. Percent change, 5.18 minus 5 divided by 5 times 100. 3.6%. So in the previous comparison, we were looking at relative amounts of acid and base, and we saw that equal amounts, equal concentrations, gives you better buffering. Here, both of these solutions have equal amounts. The ratio here is 1 to 1, but the concentrations here are 10 times smaller than over here, and so we see there's a significantly larger change in the pH. Any questions? So we can calculate the outermost points of the effective pH range for a buffer. So the lowest pH will be where the base is equal to 0.1 times the acid. So the base is 0.1 times the acid concentration. The acid is the acid concentration. A log of 0.1 is -1. And so this gives us the value of pKa -1. Down here, pH will equal pKa plus the log of the base concentration. So the base concentration is 10 times the acid concentration divided by the acid concentration. And so this will give us pKa +1. So the 0.1 here and the 10 came from our earlier determination that an effective buffer will have a ratio of acid to base that's no different than more than by, yeah, that didn't come out very well. The ratio is no more than 10. One cannot be more than 10 times as concentrated. And so that's what we end up with. So this is the effective buffer range. It's 1 pH unit on each side of whatever pKa is for the acid we're making the buffer out of. Any questions? So the effective range for a buffering system is 1 pH unit on either side of pKa. And you'll have the best effect when the pH of your buffer is equal to its pKa, meaning the concentrations are equal. So sometimes we need a buffer that has a particular pH. And so we can use this information to choose what weak acid to use for our buffering system. And if we can't find one where the pH is, where the pKa is at the pH we want, we can tweak it a little way, one way or the other, by altering the ratio of base to acid. So which acid would you combine with its sodium salt to make a solution buffered at pH 7.35? So let's answer that question first. So we want the solution to be buffered at 7.35. So what kind of a pKa are we looking for then? One that's close to 7.35, right? And so in these 4 options here, the only reasonable choice is the hypochlorous acid, because there the pKa is close to the pH that we want. This will be a good buffer between 6.54 and 8.54 on the pH scale. So if we have 500 milliliters of a 0.1 molar solution of the acid, what mass of the corresponding sodium salt do you need to make the buffer? Are you just pulling that out of the air, or are you looking at the answer on the slides?
Oh, no, I was saying because you said the most effective buffer is the one that has...
Well, yes, the most effective buffer is when you have equal amounts. But the thing is, if we have equal amounts, the pH will be 7.54. We want this pH to be 7.35. So we can't have them be equal. So we can use the Henderson-Hasselbalch equation in a different way. So we want the pH to be 7.35. That's equal to the pKa plus the log of the base over the acid. So we can solve this for that ratio at 7.35 minus 7.54. So negative 0.19 is equal to the log of base over acid. And then we're going to do the anti-log of both sides. The anti-log for base 10 is 10 to the x. So 10 to the negative 0.19 is going to be equal to 0.6457, and that is going to equal the ratio of the base concentration to the acid concentration. What's the acid concentration? It's 0.1 molar, right? So then the concentration of the base that we want to have is equal to 0.10 molar times 0.6457, which will be 0.06457 molar. Did I lose anybody? I don't believe that, but nobody's saying anything. Anybody have a question? Okay, that's very honest, thank you. Got lost somewhere, but not sure where. Okay, so let's just talk through this real quick, review. This is the pH we want. We can use the Henderson-Hasselbalch equation to find out the ratio of the acid and base concentration, because the pH of the buffer is equal to its pKa plus log of base over acid. Why did we pick this pKa? Because a buffer is effective plus or minus 1 pH unit from its pKa. So this will be effective from 6.54 to 8.54. Yeah. This one will be good from 2.74 to 4.74. All of these are just going to be in the 4 something at the highest.
Okay.
Yeah. So then, we're doing a little algebra here. Anybody want me to go over that part? We can find the ratio, and then we know the acid concentration because they told us what it is. So then we can find the base concentration. We're not done yet, though. We need to know the mass of the corresponding sodium salt to give us this concentration of the base. So, how do we figure out what the sodium salt of an acid is?
And take away the H and add Na.
Yeah, we're going to swap Na plus in for the H. Right? So, yeah. That will be NaClO. Because when you put that into water, you're going to get sodium ions and hypochlorite ions. This is the conjugate base of the weak acid. We can't just have a bunch of negative ions. The compound has to be neutral. So sodium is the counter ion. It's just keeping this company. But we need to know that because we're trying to find a mass of this. What's nice here is we're not adding a liquid, which would give us dilution issues and volume changes and blah. So we don't have to worry about that. Okay, so sodium hypochlorite, we're going to need its molar mass. So sodium is 22.99, chlorine is 35.45, oxygen is 16. .44 grams per mole. So I got this molarity here, and capital M, our brains often don't really recognize what that is. I've seen students do all kinds of crazy things with that. That is moles divided by liters. Molarity is a great conversion factor between moles of something and liters of it. So what volume of this solution are we going to have? 500 milliliters. We're going to assume that when we put the solid in there, it doesn't change the volume. It's not quite true, but we don't care. Okay, so 500 milliliters is 0.500 liters times 0.06457 moles per liter. That gets me to the moles of this sodium salt that I need. And then we're going to use the molar mass to find the mass. And my units are all going to cancel out nicely. So 0.5 times 0.06457 times 74, whoops. So 2.403 grams. We got we've got 2 sig figs in here, and that comes along in here and limits that. And so probably say that 2.4 grams is close enough. Any questions? Yeah.
You were saying that it's a plus or minus one,
Mm-hmm.
or when
Right, so a buffer will be effective at +1 or -1 of its pKa.
So, like, if it was like 3.25, that was a pH,
Mm-hmm.
could we use any of those top three, even though that middle one might be the most effective?
Yeah, so if you wanted a pH of 3.25, any of these would be appropriate. This one might be slightly better, but not really significant. But you would not be able to use this one at 3.25. Any questions? Yeah.
So, in this, you said, because we know the acid concentration, would it be the same case, just different how it's set up for the base, if we do the base concentration?
Yeah.
Okay.
Yeah, so if they said we have this solution and they gave us the base concentration and were asking us how much acid, we'd still end up with this ratio here, but then we would be solving for the acid instead of the base. That's the only difference.
Then we'd have the base divided by that ratio.
Mm-hmm. Yeah. Any questions? Got it right. So buffer capacity is how much acid or base can you add to this buffer without causing a large change in pH. So buffer capacity will increase when you increase the absolute concentrations of the buffer components. It will also increase as the relative concentrations become more similar to each other. So buffer capacity is something that we think about, but we're not going to be quantifying the buffer capacity of this or that. You just take these factors into account when you're creating a buffer. Side note here, if you are using a buffer that needs to primarily neutralize acid or primarily neutralize base, then you might want to make it a little lopsided, right? So if you know that acid is going to be added to this buffer, you might want to go a little heavier on the conjugate base. So there's more of the base because you're just expecting acid to come in. If you're just expecting base to be added, then you'd want to be a little heavy on the acid concentration. Okay, so we have a 1 liter buffer solution that's 0.1 molar in HF and 0.05 molar in NaF. Which action destroys the buffer? Adding 0.05 moles of HCl, adding 0.05 moles of sodium hydroxide, adding 0.05 moles of NaF, or none of the above. So, what are we even going to think about here? So, this is our acid, right? And that's the conjugate base. So, if we add acid to this buffer, is it going to react with the HF or with the F minus? It's going to react with the F minus. So this reacts with the NaF. And how does this amount compare to the amount of that base that's in the buffer? It's the same. So adding 0.05 moles of HCl is going to take out all of the conjugate base. Is that going to destroy the buffer? Oh yeah. So this one is going to destroy the buffer. So that leaves no base. What about here? Here we're adding hydroxide. Well, hydroxide ion would react with the acid, right? And that's the HF. So this is 0.1 molar in the acid, and we're adding 0.05 molar. So after this, you're still going to have acid, that's going to leave 0.05 molar of the HF with the 0.05 molar sodium fluoride. Is that still a buffer? Yeah, you might even say it's a better buffer now because the concentrations are equal. So that's not going to destroy it. How about adding more NaF? No, that's not going to destroy it. The concentration of NaF here is half of the acid. If we add more of it, now they're going to be equal in concentration, and the buffer's going to get better. Any questions? Yeah.
So when for case B,
Mm-hmm.
when they're taking out the HF, would it change into an AF2?
Yeah, so the way the sodium hydroxide would react with HF is it would take the hydrogen to make water, and that would create more F minus.
Okay.
Yeah.
So in that case, it'll leave the 0.050 HF and 0.1 F minus?
Approximately.
Okay.
Yeah, because then you got that equilibrium business. But yeah. Any questions? Other questions?